All right, and those other ones are precipitation reactions, okay? And this is double displacement reactions. We'll be dealing with the precipitation reactions a lot, okay? So a precipitate forms when you take two ionic compounds that are soluble in water, meaning they're just solutions, okay? They'll look clear, and you mix them and a solid forms. That's a precipitate, okay? And there are rules that govern whether an ionic compound is soluble in water. These are called solubility rules. And here they are. Oh my goodness, there are a lot of them. You must memorize all of them. Just kidding. Oh, Mr. Ryan, you're a crazy man. Where do you think you could find these? That's right on the polyatomic ion chart of science. That's amazing. Okay, here they are, the solubility rules. So, you can use this at any time. Okay, you're going to get this on all tests. So, you'll know it's right there. All right, so let's see what I'm talking about here. Okay, here, oh, good stuff all the way from the start. All right, so I've got two compounds. Now, I've given you a little information right here that these are both soluble. You can thank me in class. All right, you might have to look those up because if they're both solids, nothing happens, right? It's just crazy. All right, so now, unlike the single displacement reactions, for the double displacement reactions, you actually have to know what the products are. Do you have to know the formulas? Why, no. No, you don't. Okay? You can write in that you know that the products, this would be a double displacement reaction, right? So this one product is sodium nitrate. Okay, because I got that and that, and I got that and that. And the other one is copper, same charge, to phosphate. Okay, so now I can go to the solubility rules, all right? So, okay, the first one that I want to find is, I just want to start at the top. Salts of ammonium and group 1 elements are always soluble. Well, sodium is a group 1. It is always soluble. Yay. So this compound is soluble. All right. Now, what about this one? Copper to phosphate. Okay, so that's not a halogen. It's not a chlorate, nitrate, or acetate. There's sulfates. Phosphates. Phosphates are and carbonates are insoluble except ammonium and group 1 compounds. Okay, so sodium phosphate is soluble because it's with a group 1 compound or group 1 atom. Okay, copper 2 phosphate is going to be a solid. So this is going to be our precipitate. All right, so the formation of precipitate means that a reaction happens. So now I've got to actually make my compounds. So here's Na plus and here's NO3 minus. NaNO3. Again, you wouldn't believe how many times I've seen compounds like Na3, NO3-2. No, that is not a compound, all right? You have to do this the correct way. Get your compounds first using subscripts to balance the charge, then go back and balance your chemical compounds using coefficients. Don't try to mix the two or things will go badly. Okay, copper 2 phosphate. This is Cu2 plus, and phosphate is PO43 minus. Okay, now this one's going to be a little weird, right? Crossover method gives me 3 and 2. Okay, and so when I make the compound, that's Cu3 parentheses PO4 2. That's something. All right, so here we go. Let's balance. So phosphate remains unchanged, so I can balance that. Nitrate remains unchanged, so I can balance that. Okay, there's not really a best place to start here. you could just pick something. All right. How about the phosphates? So I know I can put a 2 in front of this. I need to put a 2 in front of sodium phosphate to balance the phosphates. Okay, which means I'm going to need to put a 6 here to balance the sodiums. Okay, which means that I'm going to need to put a 3 here in front of the copper 2 nitrate to balance those 3 coppers and those 6 nitrates. Bam! Done. Great. Okay, now, so that's one way of presenting this. Okay, this is the balanced chemical formula. All right, now I could also ask you to write the complete ionic equation. All right, and in the complete ionic equation, you write out all of the ions. It's somewhat tedious, okay, with their correct number. Now, this is going to get a little tricky, right? So I know that I have 3 copper 2 ions. Okay, and I got that from this. Nitrate has a charge of -1, there's -2, that's +2, +2. Okay, copper 2 nitrate. Nitrate ion is NO3 minus. Okay, but now I have to figure out how many of them I have. All right, so that's NO3 times 2 times 3, that's 6. Okay, plus 6 sodium ions plus 2 phosphate ions. All right. States of matter for a complete ionic equation are somewhat redundant. Okay, there is one place that they're very, very important. Okay, yields 6 sodium ions plus 6 nitrate ions plus copper 3 phosphate. Ooh, that one's a solid. It doesn't form its ions in solution, okay? So, you just write the solid there, and that's it. And everything should still be balanced, all right? So that's a complete ionic equation where you write everything out. The next thing that you would do is a net ionic equation. Okay? And that would be, the interesting thing here is that the net ionic equation is really just what takes place in the reaction. So we have to go back and we have to think about the reaction. What is the reaction? Well, it's kind of a change of state thing, right? I have 2 solutions, okay, 2 compounds that are soluble in water, and I mix them and I get a solid. So it's really the formation of this solid, okay? So I have 3 Cu2 plus 2 phosphate ions yields Cu3PO42. Okay? Now sometimes you might end up with like a 2 in front of this, which would multiply all these things by 2. Do I care for the net ionic if you reduce? No, not really. Okay? You can do it either way. It's most correct to reduce, but this is kind of a weird construct, right? So the last thing that I want to do with these is I want to identify something called spectator ions. Well, what are spectators? Spectators are just kind of watchers, right? They sit there in the stands and they watch all the action happening somewhere else, and they don't actually participate in what's going on. They just watch. All right? So spectator ions here if this is my net ionic equation, if this is the reaction that actually happens, what about the sodium ion and the nitrate ion? Oh, and did I really do that? NO3 minus. Come on. Come on, Mr. Ryan. Embarrassing. These aren't really participating in the reaction per se, okay? They start as ions, okay, in these two solutions, and they end as ions in those two solutions, okay? What they're really there for is to make the other things soluble, but they don't participate in the reaction. So my spectator ions are sodium ion and nitrate ion. Okay, I might ask you for the formula of the spectator ions. I might ask you for the name. Just be aware of what I'm asking for. All right, now this one, I want to write the balanced chemical equation, complete ionic equation, and net ionic equation, also named the spectator ions. Okay, so the first thing that I want to do is I want to make the products and make sure that a precipitate forms. Okay, so one of my products is going to be copper 2 sulfate. And my other one is going to be sodium nitrate. All right, so now I'll go to the solubility rules and I'll look up sulfates. Okay, they're down here. Sulfates are soluble except calcium, strontium, barium, mercury 1, mercury 2, lead 2, lead 3, and silver. So that is not one of those compounds, which means that this is soluble. Okay, so that's soluble. And sodium nitrate, right there, rule 1, group 1 elements are always soluble. Okay, which means that this forms a aqueous solution, and this forms an aqueous solution, which means no reaction. And that's all I'm going to ask you to show. Okay, name them. Okay, name the products, identify that they're both aqueous, and then write no reaction and you're done. And that's it for double displacement reactions using solubility rules.